Hello, everyone. My name is Liu. Today, I'm going to talk about our work Atlas, a hybrid data plane for efficient far memory applications. This is a joint work by University of Chinese Academy of Sciences, UCLA, Tsinghua University, and Microsoft Research. Memory, as one vital resource in data centers, is facing critical challenges. First, as more and more data collected and analyzed, data center workloads are becoming increasingly memory intensive. However, a growing speed imbalance between compute and memory capacity makes memory more and more precious. On the other hand, due to problems such as allocation imbalance of compute and memory resources are still underutilized. These memory challenges urge an evolution in memory architecture. One promising solution is remote memory. Remote memory is enabled by network advancements such as RDMA over InfiniBand, which allows CPU on one server to directly access the memory on another server without intervention of the OS from either side. Now, when the compute server falls short on local memory, it can utilize remote memory to expand its memory capacity while improving the CPU and the memory utilization of the whole system. However, there's still a big performance gap between local and remote memory. For example, the access latency of remote memory via RDMA is still about 50 times higher than that of local memory. As a result, to achieve optimal performance, hot data should be kept in local memory. In practice, the local memory is usually maintained as a cache. Upon access, remote data is fetched from the remote memory to the local cache, and under memory pressure, code data in the local cache is evicted to the remote memory. Based on the idea of caching, two kinds of data paths to transfer data between local and remote memory have been proposed. The main difference between them is the granularity, or the unit of data transfer between local and remote memory. One type of data path transfers data in 4 kilobyte pages, while another type transfers data in objects. On average, an object is much smaller than a page, so a page can contain dozens of objects. These two kinds of data paths have different data transfer mechanisms, and each with its pros and cons. The page-level data path piggybacks on the paging system in the OS kernel. By mapping remote memory as a swap partition of the compute server, the swap system can evict code pages, and when a remote page is accessed, a page fault is triggered to bring the page back to the local memory. The whole process is maintained by the OS virtual memory system and transparent to the application. Therefore, there is no runtime overhead. The application does not need to maintain pointer updates or data hotness information. Besides, since the page usually contains dozens of objects, page-level transfer provides a good throughput as multiple objects can be transferred with one page. However, since it must transfer all objects on the same page, it may fetch useless objects or evict hot objects, leading to a waste of network bandwidth and local memory, a problem called I/O amplification. For the object-level data path, the application runtime is redesigned to enable the transfer of individual objects. In such systems, the access to an object must go through a piece of code before the actual read or write, called the barrier. The barrier will first check whether the object is local. If it is not, the barrier will initiate a network request to copy the remote object to local memory. Since the copy changes the address of the object, all pointers to the object need to be updated to point to the new copy. Similarly, objects are also evicted individually. The runtime checks the hotness of every object. Under memory pressure, code objects are identified and evicted. When an object is evicted, all pointers to it are also updated to indicate that the object is remote now. Since the runtime path only moves one object at a time, there is no I/O amplification. However, the runtime path suffers a higher runtime overhead as it needs to perform extra operations such as pointer updates and object-level hotness tracking. Besides, if useful objects are stored contiguously on a page, while one page fault can fetch them all, object fetching can only fetch one object at a time, leading to a lower throughput. Existing systems all support only one kind of data path. The data is either transferred in objects via the runtime path or in pages via the paging path. However, one fixed data path cannot achieve optimal performance. The determining factor behind this claim is the locality. We define the locality of a contiguous memory block as the percentage of a block that is accessed close in time. When most of the block is accessed together, we consider the block to have a good locality. Otherwise, if only a small part of a block is accessed in a while, we consider its locality bad. Different memory access patterns exhibit different locality. For example, sequential access has a good locality as it touches every contiguous object in a memory block, while random access has a bad locality because it may only touch a few objects in a big memory block for a while. Clearly, we can see that when a remote block has a good locality, page fetching is more efficient as it can fetch dozens of objects that will be accessed soon with one page fault. But if it has a bad locality, object fetching is a better choice as it can eliminate amplification. On the other hand, real-world applications usually consist of multiple tasks, and the memory access pattern can dynamically change across these tasks, leading to different page locality. For example, we run a page view count application with Mattis, a map-reduced framework, and plot its page fault sequence in the figure here. We can see different memory access patterns between these two phases. The left part shows the page fault of the map phase, where items are inserted into a hash table, exhibiting a random access pattern with bad locality. While the right part shows the page faults of the reduce phase, where items in each bucket are streamed through, leading to a sequential access pattern with a good locality. Since the two paths each only feed one kind of locality, one path cannot achieve the best performance for all cases. To illustrate this observation, we run the MapReduce application on AIFM and FastSwap, which represent the state-of-the-art runtime path and the paging path, respectively. We can see from this figure that the runtime path runs much faster in the random map phase, while the paging path can perform better in the sequential reduce phase. Since one single path cannot perform well for both kinds of locality, one natural question to ask is, can one single data plane combine the advantages of both data paths to achieve optimal performance? This leads to our work Atlas, which is a hybrid data plane. Atlas consists of three components. First, a hybrid fetching path, which is capable of fetching remote object via both the runtime path and the paging path. Second, a locality profiler, which decides the fetching path for every remote access. And finally, a unified page eviction path to evict code data from the local cache to the remote memory efficiently. You can see with the hybrid design, Atlas can produce two key benefits. First, it provides optimal data transfer efficiency because it can always use the preferable path to transfer any data. Besides, the runtime path can fetch objects scattered in remote memory into a contiguous space in local cache, gradually optimizing memory locality. As a result, future accesses to the data block is more likely to use the paging path with a better efficiency. The idea of a hybrid data plane sounds promising, but to realize these goals, Atlas needs to solve three challenges. First, how to efficiently profile data locality. Next, how to enable the switching between the runtime fetching path and the page fetching path. And finally, how to synchronize between these different system components. The first challenge is how to profile data locality to distinguish data blocks with good and bad locality. Atlas chooses the size of a page as the unit of profiling, as this is the smallest size the paging path can transfer. In terms of the data to collect, we logically divide a page into many equal-sized cards and maintain an access bit for every card. The accessed bits form a bitmap for every page, called the card table. Each set bit in the card table denotes that a card has been accessed recently. To estimate the page locality, Atlas scans the card table and calculates the card access ratio for every page, which is the number of recently accessed cards divided by the total number of cards in a page. The card access ratio will act as an indicator of every page's locality. A high ratio denotes a good locality, while a low ratio denotes a bad locality. With the locality profiler, we can get the real-time locality of every page. Here, we use a blue rectangle to denote a page with good locality and a yellow rectangle to denote a page with bad locality. The next question is, how can this enable path switching? A strawman solution would use one of the two paths globally based on the percentage of pages with a good locality. For example, when more than half of the pages have a good locality, all remote accesses go through the paging path, and vice versa. However, this coarse-grained approach sacrifices the fetching performance of the pages whose locality does not fit the selected path. Therefore, Atlas decides to have fine-grained control over the fetching path of every page. To achieve this, a 1-bit path flag is maintained for every page, which is set based on the profiling result. If a page has a good locality, its flag is set to paging. Otherwise, it is set to runtime. When a remote access happens, the path flag is queried to check which path should be taken. As a result, Atlas can always use the more suitable path to fetch remote data for every page. The last challenge is synchronization between different components. There are 4 components running concurrently in an Atlas application. The application running the actual user code, the runtime fetching path, the page fetching path, and the unified eviction path. These 4 components can access or move the same object concurrently. Without proper synchronization between them, there will be data races. Therefore, Atlas maintains a set of invariants to eliminate such data races. Here, we will show 2 examples. First, the race can happen between the runtime fetching path and the page fetching path. When 2 threads aim to fetch the same remote object with the 2 paths respectively, they will end up with 2 copies of the same object. This will cause correctness issues if either object is modified later. To prevent this, Atlas maintains an invariant that at any given moment, data on the same page must go through one single fetching path. Therefore, the 2 fetching paths will never fetch the same object at the same time. Data races can also occur when an object accessible by the application is moved by the runtime path. The application accesses the object via a raw pointer, which is merely the address to the object and is unable to be updated when the object is moved. Therefore, if the object is moved by the runtime path, the raw pointer becomes a dangling pointer, causing correctness issues. To avoid this, Atlas enforces a second invariant that objects with raw pointers must be kept in local memory. As an object will only be fetched when it is remote, this invariant ensures that objects accessible by raw pointers will remain local and are never moved by the runtime path. Details on cross-component synchronization can be found in our paper. Atlas is evaluated against AIFM and FastSwap on a set of 8 applications, spanning across different memory access patterns, such as memcached with random or skewed accesses, data frame with mostly sequential accesses, as well as MapReduce and dynamic graph analytics applications with phase-changing behaviors. In terms of throughput, Atlas achieves a 3 times higher throughput than FastSwap and a 1.5 times higher throughput compared to AIFM on average across different local memory ratios. In terms of latency, Atlas reduces 90% latency of memcached by 1 to 3 orders of magnitude compared to the baselines. One major source of Atlas performance benefits comes from the ability to dynamically switch between 2 fetching paths. To showcase this ability, we run a PageRank application to track the percentage of pages taking the paging path during its execution. The PageRank application goes through periodic phases changes between graph loading and algorithm runs. Graph loading adds new edges to the adjacent list of a graph in a random pattern, while the algorithm run scans through the adjacent list of the graph with good locality. We can see that Atlas can quickly identify changes of phases and adjust the number of pages taking the paging path to improve the overall performance. In conclusion, although the object-based runtime path is considered to be more precise with fine-grained accesses, the benefits do come with performance hits. By combining the both of the runtime path and the paging path with an always-online profiler to make path selection, we can provide efficient file memory for both bulk data and scattered objects at the same time. That is all for my presentation today. Thank you, and I'm willing to take any questions.